So my name's Johnson Noel. So I've been at Hazelcast for about 4 months. Feels a lot longer, but so I'm not actually. I'll be honest with you. I'm not actually a developer, but I'm becoming one. But my background has been 32 years in the software industry, primarily around databases. So I'm talking about IMS, Kix, DB2, vSAM files, COBOL, Assembler, PL1. And then I spent 13 years at Microsoft with the SQL Server team. And since then, I've been working for a number of different startups in Silicon Valley. I've been at Hazelcast for 4 months. And today, I am going to talk to you about IMDG and JET, which is our in-memory data grid and our distributed stream processor. So these are the typical pain points that, we're hearing from our prospects, and we hear it quite a lot. So predominantly, most of these issues actually fall into one area of bottleneck, and that's latency. And I guess that's no surprise. I'm sure a lot of you are familiar with that challenge. And when I'm talking about latency, I'm not just talking about latency regarding access to data or information. I'm actually talking about latency when it comes to compute and processing capability as well. So if you think that in addition, you look at business events throughout the year, they may result in websites or applications grinding to a halt. You think about the repercussions of that, service unavailability, the damage to your reputation, the missed opportunities. And given that over the last 2 years, that accounts for 90% of all of the world's data that's being created, amounting to something in the region of about 670 to 700 exabytes, you can only imagine how much more data is going to be created in the near future and the subsequent impact that's going to actually have on your business. So here's an example. Let's have a look at credit card processing. So if you look at credit card processing, most of that time is actually spent in the network transit, right? That's where most of, you put your card into the ATM, and before you get anything back, most of that is network traffic, right? There's not much you can actually do about that. Now, the window for processing fraud rules for most card processors like PATH or PATH81 is 40 to 50 milliseconds. And after that, if they haven't yet found a problem, then they have to accept the transaction, right? The merchant is now guaranteed to get the payment, even if it's fraudulent, right? And if you think that on the busiest day of the year, whether it's the January sales or whether it's Black Friday or when Apple releases their new iPhone and you have to deal with 200 or 300 million requests in one day, you still have to process these requests within the same tiny window, right? So it isn't just about low latency, it's about low latency at scale. And so, this applies to, online commerce, in-store processing, trading, peer-to-peer payment systems as well. So at Hazelcast, these are the typical problems that we're trying to solve, and actually we're pretty successful at it as well. So we're enabling you to maintain consistently high performance and very low latency through our in-memory distributed architecture. Our architecture is designed from the ground up to support a scale-up and scale-out. So we can actually scale. We have off-heap capabilities. So if you could imagine, we support up to just over 100 gigabytes of off-heap storage. So we all know that with Java applications, you have the garbage collection process that comes in and slows down all of the system processing. We can offload that. We have that capability. And we provide clustering services. So it's not just clustering, it's load balancing, and it's completely high available. And I'll go into a little bit about that a little bit later on. So that automatically, all of that workload is managed by itself. You can add a node. If you add a node, the other members in the cluster will actually rebalance the workload, across all of the nodes equally. So you can add a node and you remove a node over time. All of them will have roughly the same amount of data. So IMDG and JET enable applications to process data in real time and continuously ask questions of that data. Data is about information and understanding. JET is about asking questions, what if scenarios. And when you're looking at grid use cases, if you're going to be going out into the marketplace and wanting to quantify exactly what it is you want or what kind of characteristics they should have, then these are the typical kind of things that we're thinking about. So the caching capability should enable instantaneous access to that data without unnecessary network hops and large amounts of IOPS to disk. So it needs to be highly available, fault-tolerant, and portable to whatever environment that you choose, be it bare metal or any kind of cloud infrastructure, whether it's AWS, GCP, or Azure, or any private cloud. You want to be able to support distributed computation on that data, supporting many different data structures, whether it's maps, queues, sets, locks, topics, etc. And it needs to be load balanced, and it needs to be scalable. You also need it to support microservices architectures. So, low latency applications need to be flexible with the environment that they're working with. And so you want a solution that enables you to embed those grid characteristics into your system. And you also need to be able to scale web applications and web sessions, supporting failover between different sessions, integration with web services, and any web scale-out capabilities as well. So this is what our in-memory platform actually looks like. This is at the core of the Hazelcast ecosystem. And by the way, this is at the core of the Hazelcast ecosystem, but we also have cloud services as well. And I won't be covering that, but it's another part of our ecosystem that enables you to configure a client, whether it's in Java or Python, and you can, in the space of about 4 minutes, actually create a cluster that you can actually use. If you're interested, I'll forward on some information or make sure that it gets to you at some point in time. So our in-memory data grid enables you to do lots of things, right? And one of the things that enables you to do is to integrate with systems and services. It enables you to communicate, maybe even connect and store data, and it scales using clustering and cloud solutions, supports data replication, and it's highly available. Our in-memory stream processor ingests data from a variety of different data sources. It performs data streaming, supporting time and event-based processing. You can perform ETL processes like you would do with the traditional data warehousing, extract, transfer, and load process. You can combine data, you can compute, and you can actually generate alerts. And we've actually got some use cases that I'm going to tell you about a little bit later. So we can ingest any kind of data from any data source, whether it be social media, whether it's feeds, apps, devices, and so forth. So just so you're aware, so the enterprise features are in blue and the open source features are in orange. And I've got to say, we have a lot of customers who run the enterprise version, and we have a large number of customers who run open source. And the open source version, we have a lot of customers who actually say the open source version is absolutely lightning fast. The difference is you don't get the mission critical packaging around it, like the hot restart capability, WAN replication, some of the HD features, so that you offload the heap storage and so forth. And it's no surprise, caches typically go in between applications and data sources, and this is where we sit from an architectural perspective. So your application will call Hazelcast IMDG, and we'll offload that data from a variety of data sources, and we'll process that extremely fast in our cache layer, which is highly scalable. So the real beauty of having this kind of a solution is it addresses the challenge of trying to figure out how to scale the other components, right? I've worked with databases for more than 20 years, and I can tell you it's difficult to scale a database, and it's even more difficult to scale a mainframe, I can promise you. So when the volume of data increases or the processing becomes more complex, you can just add nodes to IMDG, and IMDG will rebalance the data, and you won't have to worry about the increased latencies due to data volumes. So in terms of compute capability, because the compute occurs where the data is, we have partition-aware compute, and that means that the logic is executed in the same location as the data. So that eliminates a lot of moving of data across the network. We've talked about the network impact in terms of latency, and that reduces it substantially. And within Hazelcast, you can actually determine, so let's say you've got a 10-node cluster, you can actually determine how many of those nodes are going to be there just for compute capability, as opposed to, for storing and processing data. So we also support messaging using a publisher and subscriber model. So this is another aspect of low latency, the need for applications to be able to publish and subscribe and deliver data. So these applications, as you can see, can publish a message onto a topic, which will then be distributed to all instances of the applications that have subscribed to that topic. And one of the primary benefits of this style of messaging is that can be reliably scaled to many different nodes. So you can actually scale that out. So you're increasing the throughput of those messages. So some real-world examples as to why we choose low-latency grids. So in this example, we're executing trades. And if you're executing trades, you require low latency to access to lots of different types of data in order to calculate and run trades within a tiny window, right? And those processes need to be able to aggregate market data to provide very fast access to prices and market calculations. So if you're performing those calculations on a data grid, you can perform them at scale and then provide very low latency access to the output, the consumers of those calculations. These are actually two real-world examples and quotable. You can get online, you can have a look at them. So HSBC is using our grid, IMDG, for their FX quotation systems, and National Australia Bank are using IMDG for their market data aggregation processing. So in terms of payments and card processing, Capital One are actually performing distributed computation on 20,000 card transactions per second, and they're doing that in less than 1 millisecond latency. So their architecture, by the way, also supports 5 nines uptime, and they're processing 2 terabytes worth of data. And, that's a lot of data. I know, we're into the exabytes now, but when you're talking about real-time processing, when you're talking about less than 1 millisecond transaction throughput, I think that's, it's pretty impressive, right? And Visa, they're processing 10,000 transactions per second, and they have got SSL encryption switched on. They are also supporting 5 nines uptime, and actually, this is what they tell us, not what we say. they've actually told us that we were 2 to 3 times faster than Redis, and that was for that very specific use case. There are a number of different grids out here, and all of them have got their virtues. In this occasion, Visa were able to prove that. So online commerce is another area where low latency absolutely matters. And, Apple and Target are two of our customers, and they are examples of customers who needed very, very low latency with high levels of scale and the ability to have their online stores respond really, really quickly. In Apple's case, they actually moved on to Hazelcast IMDG from an alternative grid that will remain nameless, as they found that the complexity of managing the environment ultimately led to downtime. So it's not just about providing that scale to offload data, to process it in sub-millisecond transactions and present back to the client or to other consumers or processes. It's about having that available all of the time, having zero downtime, having an infrastructure and services that will always maintain the system 24/7. Another example, so Comcast, this is a great example. So they use Hazelcast to actually drive their chatbots. And so these chatbots are obviously pretending to be a person. I'm assuming no one's surprised by that. And will eventually offload to a real person. So, prior to the handover, they're asking questions like, have you reset this? Have you switched that on? Have you configured this to this value? Or whatever it is. They've used the chatbot to actually replace their voice recognition system. So that chatbot needs to have all of that information instantaneously available for it to be a realistic and positive experience, right? So it needs to be able to respond in real time and to give the customer, the best experience possible. So that was IMDG. Let's talk a little bit about stream processing. So another challenge that we actually see in the marketplace today, so we've talked about the huge data growth due to IoT devices, sensors, social media, smart technology. Well, what about if you want to make sense of all of that data and determine how much value you can derive from it, right? So historically, organizations would have data scientists, they'd be shifting through long batch processes until they found these nuggets of information. Sometimes those batches would fail and you'd run incomplete data, or sometimes they wouldn't run at all, right? So in the very late 80s, I was the guy who was responsible for, the TPS report, and there were all sorts of things that would happen, right? The batch process would fail. If you called someone at 3 a.m, they would just tell you to delete records from this live system, and then you just rerun it, and then of course all of that important information would be lost, and then you'd have to wait the following day. This problem existed for quite a long time. And of course now, today's leading organizations need perishable insights, right? If you don't act on them instantaneously, the opportunity is lost, or the risk isn't avoided. So a good example of that is in this diagram. We're showing the sat-nav information highlighting the traffic jam ahead. That information is only useful to you when you're traveling between those 2 points, and that's where real-time stream processing really comes into its own. So when we look at the evolution of stream processing, if you look at the early days, they had very, very fast processing, but it was hard to maintain. And even though it was distributed processing, it was typically batch-oriented. And then once we moved into the second generation, you had the likes of Apache Spark, which enabled some kind of micro-batch stream processing. But it wasn't real stream processing. It was, and neither was it low latency either. It was complex to manage, and it required dedicated environments. And so third generation introduced distributed real-time stream processing with advanced techniques for distributing the compute with much more flexibility. And that's where Jet actually sits. It also has an additional advantage by being an in-memory platform offering the lowest latency and the highest performance. So Jet and IMDG, they can be exclusive, but actually they work hand in hand really, really well together. So talking of low latency, not every stream processor has low latency. So here's a comparison. All of the information about this in comparison is online in terms of how it was configured, how it was set up, what servers were used, everything. It's all available. So what you can actually see is that we have the lowest latency, and that's really, really important, right, for real-time stream use cases. After an item, after a record has been ingested, how fast can I get the results, and actually what can I do with it? The latency of Jet remains low at scale. So if you have a look at it, as you go from 10,000 all the way up to 5 million, our scale actually is very, very low. And this is due to a number of things. A couple of them are due to the windowing design and the way it's actually been designed, and actually how we distribute the workload across each of the nodes in that cluster. So if you could imagine, Jet in itself is actually sitting on a cluster, and all of the processing operations are actually done on each member in that cluster, and then we bring that data together, and then we push it back to the recipient, whether it's another client or some other process. In this example, by the way, Jet was running on its own. There was no IMDG underneath this, and each vendor tuned their applications as much as they could in terms of processor affinitizing, making sure workloads were processing as close to the client as possible, and other tricks. So it was a fair benchmark. And so with low latency, you can effectively store things like ML training on the grid and models, and you can pull that into the data in motion to do things like predictions, and you can be proactive with how you actually respond to data in real time. And I've got a great example regarding this a little bit later on. So I've talked about the two components. I've mentioned that they work together. Jet, our in-memory distributed stream processor, and IMDG, our in-memory distributed data at rest. And when you run them side by side, you're able to pull data from a variety of different data sources, make changes, and then push them through our stream processor so that they can be contextualized, right? And used for other services. And we've talked about analytics and machine learning. So this is data that's continuously moving and changing, and we're enabling you to query that data in real time. Imagine it's record by record. You're taking a record, you're processing it, you're doing something with it, you're enriching it, you're changing it, you're classifying it, and then you're pushing it somewhere else. Just some of the usual, the typical use cases that we use Jet for. I'm not going to go too much into this, but we talked about ETL, ingesting data, change data capture. We actually do work with a lot of customers who've got big mainframes, and what they're actually doing is they're sucking all this data off the mainframe, they're processing it in IMDG, and then they have a variety of different consumers. So someone else might want to do reporting, someone else wants to do training, and they're using Jet to actually pull that data, denormalize it for data warehousing, and do all kinds of enrichment and classification, so they put some context and richness around the data. So here's how a data grid and a stream processor can work together on the same platform. So, we've talked about ingesting that data and providing enrichment. But this is what you get, right? You add context to enrich, you add meaning to classify, and you can merge data and, do training in order to do some kinds of predictions. And I'm going to talk a little bit about that. Now, these slides, the next few slides weren't in the original deck, but I decided to add them in there because I kind of figure that most people understood what a data grid looks like. It sits in between your application and your database. A stream processor, a little bit different, I guess. So, JET is based on what's called a direct acyclic graph framework. Now, historically, DAGs came out of mathematics, but it's now been used to process flow in computer science. And the real value of DAGs is it avoids looping. You need to think about it like it's akin to an assembly line process where a product goes from one side of the assembly line to the other, being modified as it passes through each stage, and you're avoiding deadlock loops. That's the real value of DAGs, and most enterprise stream processors will use that framework. So the circles represent vertices or the processing piece. Each vertex is a step in the computational flow. So in your code, when you call the JET instance, you would also define a DAG, and then you would build your logic around that DAG. A really simple word count just to kind of give you a sense of how it all works. So what we're going to do here is we are going to process each line. We're then going to split that into words, and then we're going to update the counts of each word. And if we represent this DAG, if we represent this as a DAG, we can actually tokenize the words and start accumulating the totals for each one, right? So the source and the sink is input and output. As I go through the next few slides, you'll see how we're actually breaking this down and how JET enables you to throttle how your work actually goes through the flow of the system and really give you a lot of control. So in this example, each vertex can operate at its own speed, and it's using the concurrent queue to buffer the workload. So the blue blocks run in memory on the same server as JET because it's built on the IMDG platform. And you can now distribute this computation and start scaling elastically. So as we parallelize this across CPUs and clusters, we can benefit from linear volume increases. So all of the nodes need to agree on who owns what partition. The data is processed locally, and then it's sent to the partition owner as part of the combiner step. And remember I talked about the JET Spark Flink thing? This is essentially what we're actually doing, processing the data locally and then sending it back to the partition owner, so to actually combine the values together. So, we can now scale this across the cluster. All nodes are working concurrently to process the workload. And so we have it's known as a cooperative work model. So this is better than the typical kind of master worker approach, right? Because each one is looking at the other nodes, and we're pulling work from the other nodes. In a master worker model, the master has to actually be available in order to schedule the work to the other available nodes. So when we talk about low latency and performance, all of these design decisions, these architectural decisions in the product have made the difference in terms of high performance. I want to talk a little bit about windowing and how we've actually designed that in JET as well. So sometimes you want to look at events in discrete chunks, right? Or you want to do some kind of aggregation or join. Sometimes these windows are staggered, but they don't overlap. So slide in windows, move, but can overlap. Window in is about executing from one chunk of data to the next. So you can also use window in to cater for non-events. So you can also figure out whether something was supposed to happen, but it didn't happen as well. And we can also refit that data that doesn't belong in the right window. So data that's been processed late, if it can't be fitted within the boundaries or within the constraints defined. So if you look at this example here, number 2 has arrived so late that it's missed an opportunity to be resequenced. So we can do something about that. We can actually process that as an exception, or we can build some rules and logic as to, under these circumstances, what do you actually want to do about these stream processes. And this is really all about job elasticity. When I talked about 5 nines and I talked about processing availability and some of the other great things that give you a 24/7, 365 system, these jobs are elastic. They can dynamically scale to make use of all available numbers. You can have automatic re-execution of part of the jobs in the event of a failed worker. And it's completely tolerant in terms of loss of nodes. Assuming you lose one of your nodes, the workload will be rebalanced and it will actually be recovered from the last snapshot. So we enable you to have snapshots so you can actually build in resilience within your system. So let's look at a streaming use case. So this use case represents payment processing information. So as you can see, you have your payment values, the locations where these payments took place, account balances, and payment history. And you want to be able to ask questions of that data, present what-if scenarios, and so forth. So to answer these questions, you want to enrich that data with metadata and subsequently identify fraud, mitigate credit risk, perhaps even offer new opportunities and upsell as well. CGI, one of our customers, is a real use case. So they use, they actually do the payment processing for Deutsche Bank. So they needed a payment system to process payment requests, and it needed to be verified and pushed through fraud detection rules and algorithms with the minimum amount of latency, 24/7, 7 days a week. No downtime whatsoever. So going back to the DAGs and how I actually showed you how we could actually scale them out, they're using multiple jet processors, and these are pipeline components with IMDG distributed maps, pulling in the data and then using messaging to process each one of these steps. So this is a IoT use case. So this is an interesting one. So this is the monitoring of an oil platform. So you may need to handle 50,000 events per second running in a decentralized architecture, right? Because you've got oil rigs in the middle of nowhere. It needs to be decentralized. You need to also have a very low latency to adjust the pumping rate of an exploration drill. So if you can imagine, you've got all of these drills drilling away, and the most expensive part of that operation isn't actually the running of the drills. It's actually the starting and the stopping. So they need to have these drills running as efficiently as possible because they're incredibly expensive. So architecturally, we can deploy a jet cluster that's closer to the edge for low latency, and then a centralized jet cluster providing a single view of operations. So we've actually got a jet cluster running on that truck, and it's handling about 50,000 events per second, and it's situated close enough to the rig to perform adjustments to the setting of the rig. So the real value is that Jet is able to adjust the settings. The information comes in, sensor information, it comes into Jet. We have machine learning and we have rules that are actually being processed in real time, and then that's sending instructions back to the drill, and it's adjusting the speed of it, perhaps how hard it's pushing in terms of how hard it's pumping into the earth. And this is actually a real use case. So the customer is Sigma Stream. This is what they needed, a low latency solution to detect issues very quickly and be able to remedy that issue to avoid production loss and maintain productivity. So they're using Jet to process sensor data from monitoring systems and to make adjustment settings in real time. So they also had IMDG deployed in an embedded configuration. So in smaller batches, they embedded IMDG within their own microservices as well. And all of that information is online in terms of use cases and how things were configured and customer information. That's essentially the end of my presentation. All of the information that I've provided here are real-world situations. They are all use cases that are live and in production right now. Thank you for your time today. I hope you found it useful. By the way, there's some Jet training tomorrow. I believe it's free. If you see one of my colleagues, I've got a couple of colleagues here from Hazelcast, come and talk to us. We'll probably be around for a little time this evening. I can get you some more information on that. So, are there any questions? Alrighty. Well, thank you very much for your time. I hope you have a nice evening, and I hope the whole event has been successful for you in terms of, giving you some insight into what people are actually doing with in-memory compute technology. Thank you very much.